Okay, so let's continue. We had a Markus from IQOQI before the break. We have another Markus from IQOQI after the break. So Markus Müller will speak about quantum theory and the structure of space-time in the light of operationalism.
Okay, thank you. So I already learned that I should probably go to this side and not go too close to that part here. So thanks to Philip for organizing this very nice workshop. I will speak about some work that's jointly with a couple of other people that I will mention during the talk. It is about quantum theory and the structure of space-time and what we can learn about this by using operationalism. So just as a slogan, maybe one slide of what's happening in the next hour, then this is what's happening. So I'm not talking about quantum gravity directly, but it is a motivation. So quantum gravity is about a unification of general relativity and quantum theory. But what we can do, and I will argue like this in the next 45 minutes, is that we can actually study the relation of these two parts, so say of space-time and quantum theory, without actually committing to a specific approach to quantum gravity by operationalism. Operationalism is very much quantum information motivated. So we're asking how physicists communicate, how they find their way in a world where you have detector clicks and maybe you have space-time structures. So here's a quick outline of the talk. There will be some thought experiments that are pretty easy, but to prepare for those, I will have to prepare a little bit in the first part. Because when I say there's a relation between space-time and quantum theory, then we need to understand how both of these things could be different. And we typically know how space-time could have a different structure, but normally we do not know how quantum theory could be different. And my first part will be about this. How can we talk about probabilistic theories that are somehow more general than quantum? And having done that, I will in the second part go to some joint work with Andy Garner and Oscar Dalston, where we show that we can understand the structure of the quantum bit, mainly from relativity of simultaneity. And I will also talk about some work in progress with Marius, who is in the back here, on the Bell correlations and how they are related to the space-time structure. The third part will be joint work with Philip Höhn on how we can understand maybe the Lorentz group from quantum communication in some sense, and I will go to that. Okay, so let's look at the first part. What is a probabilistic theory? How could physics be different from quantum? Well, let's first look at quantum theory in a very pragmatic way, in a quantum information way. And when you do this and you ask, well, what is actually a quantum state? Then in a pragmatic way, the quantum state is the thing that allows us, well, to compute probabilities. Yeah? Or in other words, it's the thing that allows us to determine for all possible questions that we may decide a physical system to ask, the probabilities of finding certain answers. Regardless what your favorite interpretation of quantum theory is, this is a part that you will probably agree with. And here's a very simple example. If you have a spin 1/2 particle, then the question that you can ask to the quantum system is the spin up in z direction, yes or no? And we know that the probability of yes will, in this case, and in all other cases in quantum theory, just be determined by the trace of your state with an operator. So then, if you know what a state is, then what is a Hilbert space, or what is a state space? Well, it's just the collection of all possible states. So the collection of all states where the system could possibly be in. And an important property is that this is closed undertaking mixtures. So you can always think of doing something like that. You can say, maybe I prepare state psi, maybe I prepare state phi, but let's do it randomly. Suppose you do it with probability 1/2, you prepare psi, probability 1/2, you prepare phi. Then we know that this corresponds to a density matrix in quantum theory. Okay, so these are minimal ingredients of quantum theory that we can simply generalize. Instead of a quantum state, we can more generally talk about the state of a physical system in the probabilistic context. We can say, well, a state in general is just meant to be the thing that allows to determine for all possible questions that we may decide a physical system to ask, the probabilities of finding the possible answers. Well, I haven't said anything new, so that's the same that it was in quantum theory. But it doesn't necessarily have to be a density matrix or a state vector anymore. Now, instead of asking what is a Hilbert space, or instead of writing down a space of density matrices or state vectors, we can say, let's write down a state space. And then what is a state space? Well, state space is just a collection of all the states that a system could possibly be in. And we also demand that we can take mixtures. So suppose as a state, another state, there is a way to say that we prepare one or the other with 50-50 probability, for example, and then we would say we get a new state, which is a convex mixture of the two other states. So in the end, what we get when we write this down in more detail is basically a landscape of theories or landscape of state spaces that fit the description that I've given so far. So you have quantum theory, there's classical probability theory, there are things called Z-star algebras, and then there are all other kinds of beasts like quaternionic quantum theory and something called box world, and I will come back to that in a minute. So this is a bit like the landscape of geometric theories that you may be familiar with, where we say, well, you know, geometry could be different, it could be a Minkowski space-time, but it could also have torsion or have some other kind of geometry, and so on. So here we have a landscape of not theories of geometry, but theories of probability in some sense. So let's look at some mathematical details, how we deal with this. And this will not be too difficult details, and it's more meant to set the stage for the thought experiments that are coming later on. And I will use operational language. I will talk about preparations, measurements in a laboratory. Let me just say that this is not the only interpretation that you can put on this framework. You can also say it's a Bayesian framework or so. But for clarity, I will just use operational language. Good. Now, how do you describe one of these general probabilistic theories? It turns out that essentially, state spaces will be arbitrary convex sets. Like this is a convex set in some vector space over the real numbers. And so why is that? So think of a typical laboratory situation. So here you would have a device, which is a preparation device. Whenever you press a button, maybe out comes a particle or some physical system that you consider as being prepared in some state. Then you can have transformation devices where a state comes in and another final state goes out. Could be time evolution or applying a magnetic field, whatever you want. And then in the end, what you want is you want a measurement with a classical outcome that you can record and publish in PRL or so, right? So you have these three stages of a laboratory experiment. Now, just to see how that plays out in the mathematical structure, the simplest example would be a classical coin toss. In the classical coin toss, you would say, well, you push the button, and what you get is a coin which is heads or tails with some probability. And maybe the coin is put into a box so that you don't see it. Then the transformation device, what could it be? Well, for example, it could take the coin and invert it. Put heads to tails and tails to heads, for example. And in the end, your measurement device, well, there are not so many measurement devices for a single coin. Basically, you can look whether it's heads or whether it's tails, and maybe if it's tails, you have a green light flashing here, which is your outcome. And here you have always two outcomes. So the mathematical description would be the following. You say, well, my state is just given by a probability of having heads, a probability of obtaining tails. So it's a vector with these two components, probability vector. What is the state space? Well, it's just the set of all those probability vectors, and it can be depicted like this. So here's the fair coin with probability 1/2, 1/2. Here's one where you have always heads, probability 1, and here's a coin where you have always tails with probability 1, and you get all the statistical mixtures. So this is the set of possible states of a classical probabilistic coin. What do transformations do? Well, if it does what I just said, maps heads to tails, tails to heads, then it takes the vector and flips the entries. So you can think of the state space just being turned on its head. So this is a linear map, and it maps an ingoing state to an outgoing state. What about measurements? Well, if you look at a single outcome, for example, the outcome tail, then this outcome has a certain probability, and this probability must depend linearly on your state. Here it's very simple. So if I have a state omega, this one here, what's the probability that I get heads? Well, it's just P, right? This is the probability of heads. And you can get it from the vector just by inner product. Inner product with this other vector, E, that actually describes the measurement outcome. So outcomes of measurements are linear functionals, basically, on these state spaces. And this applies very well the same way to quantum theory. If your quantum state, that is, your physical system that is prepared now by the preparation device is the internal degree of freedom of a spin 1/2 particle, then you simply say, well, now my state can be a superposition of up and down, or more generally, a mixed state omega. So omega is now, the state is now a 2x2 density matrix. And if you draw a picture of your state space, then what you get, and I think most of you will know that, is a so-called Bloch ball. Quantum information people know that for a long time, but it's just a parametrization of your states, where you have two angles, phi and theta, that are there to parameterize the pure state. So the pure states would lie on the surface of this ball, and the mixed states are in the interior. So this is the state space of the spin 1/2 particle, a three-dimensional ball, basically. Transformations could just be unitaries, for example. And a unitary, if you ask in this picture what it does to the Bloch ball, then it really just rotates the Bloch ball. Yeah. And when you ask, how do I compute the measurement outcome probability, so I measure maybe spin in some direction, what's the probability of spin up? Well, it's just the overlap, the inner product, the trace inner product of the state with some other operator. So again, it's a linear functional. So both cases are mathematically very similar. And so in general, you would say, well, if I generalize this description, I just have some kind of state space, omega, whatever that is, and there are some states inside. And since we can always have fluctuations in the preparation, so here's a colorful picture where you randomly prepare a state by rolling a die, yeah? We know that we must always be able to prepare mixtures. And in this picture, it just means that your state space should be a convex set, so that all statistical mixtures of two states are also possible states. Now, this is basically all that we get as constraints. It's a very general setup. It turns out in quantum theory, if you have an n-level quantum theory state space, it's really just the density matrices that you have as your state space. Classical probability theory, as I've shown you, would just be the discrete probability vectors with n outcomes. Yeah? Positive numbers that sum up to 1. All right, now, if you know this picture of the state space, you can already learn a lot. Here's a few examples. So I've shown you the classical bit, the classical coin. You had one configuration and the other one and the statistical mixtures. The quantum bit is given by this Bloch ball, a three-dimensional ball. It looks like this. Now, a classical three-level system, if you have three classical configurations, then you have here 1, 2, 3, and all the statistical mixtures. So that would look like a triangle. Yeah, it's just three outcome probability distributions. It's this kind of simplex that you get. Now, this is quite funny. If you look at quantum theory, three outcome set of states, the 3x3 density matrices, this is a quite funny shape. It's very complicated. It's an 8-dimensional thing, if you just count how many parameters you have in your density matrix. And it's not a ball. It's some convex set with lots of symmetries and then flat pieces on the boundary, and so on. And here in this framework, you can, in principle, have any kinds of state spaces, maybe a G-bit, there's like a square state space that has been studied in quantum cryptography for several reasons, or something else. Okay, now, here's again this landscape of theories, and we're all familiar with classical probability theory, where the state spaces are basically these simplices that I've shown you. Quantum theory, where the state spaces are these density matrix state spaces. Then people like Adler and other people have talked about quaternionic quantum theory. What if you allow quaternionic amplitudes? And you can do that, and it turns out that in this case, the two-level system will also be a ball, but not three-dimensional anymore, but it will have 5 degrees of freedom. So it will be a 5-dimensional ball because you have extra phases. And you have all these other kinds of state spaces. Okay. Now, first thing to see is what would that mean? So of course we think quantum theory applies to physics. And all these other beasts do not apply. But if they did, how would physics be different? What would we see in the laboratory? And here's one example that people have studied a lot. So what you could have is you could have beyond quantum Bell inequality violations. This is a very abstract scenario, just a picture of a Bell scenario. Think of an entangled quantum state here, which is this box. Think of Alice and Bob being very far away in the laboratories, and Alice can choose to do a spin measurement. Maybe if she chooses the variable a to be 0, it will be a spin measurement in x direction. And variable, if she chooses a equal to 1, this will be a measurement in z direction, for example. And then she gets an outcome plus or minus 1. Same for Bob. And there's an abstract picture of that. Now, within quantum physics, situations like this are just described by the following. So you have a quantum state on AB, rho AB, and then you have local projection operators. And the trace of these two give you the outcome probabilities. The probability of the two outcomes, x and y, given the two settings a and b. In classical physics, this would be a different formula. You would get an equation like that you find also in Bell's work, for example. You say, I have some lambda, which is the variable that has been distributed to the two parties before the experiment, and then I have local response functions that tell me locally what my outcomes are. Both quantum and classical physics satisfy one important principle, which is the no signaling principle. That means what Alice in her lab sees locally will not depend on Bob's choice of measurement. So if you compute the marginal for Alice, then this probability is independent of Bob's choice B. And this is, of course, very important because if that was violated, they could be very, very far away. And then by choosing locally a measurement, Bob could change Alice's probabilities, and so he could signal to Alice instantaneously. But this is not possible, so the no signaling principle tells you that there is no way to signal instantaneously just by measuring locally on a state. Now, the difference between classical and quantum is captured in the Bell inequalities, for example, the CH-SH Bell inequality. And the scenario that I've just shown you, what you can do is you can compute these correlators. So given two settings, take the outcomes, plus and minus 1, multiply them together, and then you get the correlators here. And then if you compute this expression, in the classical case, you always find something that's upper bounded by 2. But we know all very well that in quantum theory, you can violate this, and you can get a larger value. You can actually get up to 2 square root of 2 in this scenario. Now, in the 90s, Popescu and Rohrlich asked a quite natural question, I think. They asked, well, is that the most general situation possible if I assume no signaling? So in other words, are quantum correlations the most general correlations that violate Bell inequalities, that go beyond what's classically possible, but that are still non-signaling and do not allow to send information by measuring? And the maybe surprising answer is that the answer is no. You can write down correlations, so-called Popescu-Rohrlich box correlations, which are non-signaling, but they cannot be satisfied. They cannot be built within quantum theory. And here's a very simple example. So a correlation is really just a probability table. And I can now just give you this probability table, what a PR box correlation is. And here it is. So you say, well, suppose Alice and Bob, they both decide to do measurement number 1. And then what they get is anti-correlation. So they either get outcome +1 and -1, Alice +1, Bob -1, or the other way around, both with probability 1/2, anti-correlation. In all other cases, for example, if they decide to do measurement 0 for Alice, measurement 1 for Bob, they get perfect correlation. Now, if you look at this table, you will find that it does not allow for signaling, but it turns out that the CH-SH Bell inequality value is actually 4. So it's even larger than the best value that you could get within quantum theory. So it turns out that there is, beyond quantum mechanics, you can have even more general non-signaling correlations. And then you can draw a little polytope. You can say, here are the classical correlations, which is actually a polytope. Here, the red one is all the non-signaling correlations, and the set of quantum Bell correlations lies strangely in between the two. It's a very strange curved shape that interpolates between these two extremes. Good. So this is a way in which physics could be different, because it turns out that these non-signaling correlations, these strange, more than quantum, non-local boxes, they appear as states, as actual states in some of those theories. For example, in a theory called box world, you will find these stronger than quantum correlations. Good. So this is basically, in a nutshell, probabilistic theories, and one example how physics could be different if another theory rather than quantum theory applied. And now I would go to the second part, unless there are specific questions for the first one.
So from this perspective, is there any way to see in which sense quantum mechanics is special?
Yes, this is a very natural question. And then you can try to answer this question by different means. One way is to say, let's write down a couple of principles or postulates for such a theory that you find physically reasonable. And then you can maybe prove that only quantum theory satisfies these additional principles.
Okay, but then you add additional structure.
Yes. And people have done this quite successfully. So Lucien Hardy was one of the first people who did this in a modern language. Also people here in the audience have worked on this. So there's Philip as well, myself, and so on. Now, as you already might guess, where I'm going to is to say, are there any constraints that follow from space-time on how these state spaces can look like, and vice versa? This is where I want to go. And in fact, the second part is about a very simple thought experiment that tells you that there are some constraints actually from relativity of simultaneity on what your bit, your two-level state space can look like. So let's look at the quantum bit. Now, it turns out that if you have a two-level system, two outcomes, then it's very natural to assume that the state space is a Euclidean ball of some dimension. For example, a classical bit that we've seen before is actually a one-dimensional ball. Yeah? The quantum bit, as we know it, is a three-dimensional ball state space. And from many arguments, you can easily get that you would physically expect that bits are always balls. So you can, for example, say, well, if I have a ball, I can always have a state, and then have a state on the other side, and these are the two states that I can distinguish. Or I can decide to do a measurement that distinguishes this state from that state, but no more than that. You can only distinguish two states, which is why this is a bit. In fact, people have talked about quaternionic quantum mechanics or octonionic quantum mechanics and beasts like this. And it turns out that in all these theories, bits are also balls. Quaternionic quantum theory has a five-dimensional Bloch ball. Octonionic quantum theory, if you take that seriously, would have a nine-dimensional Bloch ball. But in general, you could have any dimension, any number of degree of freedom of your state space that describes a bit. Now the natural question, why is d equal to 3? Why does the bit of our physical world seem to have 3 degrees of freedom and not more or less? And here's another way to phrase it. You can ask, why does our world's bit state space have exactly 3 independent, incompatible measurements? These 3 degrees of freedom of the ball just correspond to expectation values of the 3 Pauli operators. Why don't we have more Pauli operators or less? Now what I'm claiming here is that relativity theory gives you constraints on what this number of degrees of freedom could be. And this is a very simple thought experiment here in this paper with Andy Garner and Oscar Dalston, where we think of an idealized Stern-Gerlach interferometer without assuming all of quantum theory. We're saying we have an upper path and we have a lower path, and then we think of a particle that can be either up or down. So we have 2 alternatives, which is a bit. And so let's take a d-dimensional Bloch sphere or Bloch ball to describe the possible states of the particle. So what would that mean? Well, it would mean, for example, if we know for sure that the particle is up here, then this would correspond to the north pole state of your Bloch ball, or like the zero state in quantum theory, the pure state. If it's definitely in the lower branch, this would correspond to the south pole state, like the one state, the other orthogonal pure state in quantum theory. But then there are these cases where we don't really know, and if we measured here to find it here or there would be a certain probability to find it in one branch or the other, and maybe this probability is 1/2, 1/2, then this would correspond to any possible state on the Bloch, on the equator here, for example. And this must be because probabilities are linear, and if you ask about the probability of finding a particle in the upper branch, there must be some linear function of the ball. It's 1 for the North Pole, 0 for the South Pole, so it must be this here. Take the Z component, 0 would be the equator, and then you would probably do 1/2, 1/2, for example, for equator states. Good. Now, let's ask a bit more. Maybe we have a physicist that's sitting up here, and the physicist can do something to the interferometer. For example, put a piece of glass inside this arm here. And now, what are those? Let's ask, what are these transformations that he can do in one arm? And suppose you don't want information loss, you don't want to annihilate your particle, for example. What could that be? Well, so if it's a map that maps the ball into itself, and it's linear, then it must just be some rotation of this Bloch ball. Same way as a unitary in quantum theory is also a rotation of your Bloch ball. And if you do it in one arm only, then it cannot change the probability of finding the particle here. It cannot move the particle downwards or upwards. So the probability of having the particle up here must be preserved. Okay? But the probability of finding the particle up here is really just the Z coordinate here. So this means that the rotation must preserve the Z-axis. So, and you can ask not only the same for one arm, but you can have another physicist far away in the other arm, and she does also an operation, and then the same will apply to the other physicist, Bob. And we ask, what can she do to the state? It will be some transformation that rotates the ball and preserves the Z-axis. Now, what are the most general transformations where you rotate in d dimensions and preserve one axis? Well, it's just SOD minus 1. Yeah, it's like rotation group of one dimension less, where you preserve one axis. And let's assume that indeed these are the only constraints. So Alice in her arm, Bob in his arm can actually perform all these transformations. It's the most general case. Now, so far, this is all very fine, but here comes another constraint, and now comes relativity into play. So relativity tells you that you can fly by in a spaceship and look at the setup. And if you're in one particular frame of reference, then you will see that in the setup, actually, it's when you ask what happens first, is it TA or TB, then if these are the lines of simultaneity, then TA will happen first, and then will TB happen. But there's another frame of reference, because these are space-like separated, in which it's just the other way around. But observers should agree on probabilities of clicks. And for that to be guaranteed for all states, it must be that these transformations that you can do locally, that they all commute. It doesn't matter which one happens first. So you can see that all transformations in the rotation group of dimension d minus 1 commute. But we know that only in 2 dimensions do all rotations commute. So d minus 1 can be at most 2, which tells you that d itself can be at most 3, and there can be at most 3 degrees of freedom in your Bloch ball, and not more. Now, I've made this very strong assumption here that all these rotations of the ball can be done by Alice and by Bob. Let's make a bit of a weaker assumption. Let's say whatever Alice and whatever Bob can do, these are isomorphic transformations in some sense. So for every device for Alice, there's a corresponding device for Bob. And then it turns out that you can get a bit more. You can get up to dimension 5. So you can also have a ball, a Bloch ball, which resembles, for example, quaternionic quantum mechanics. And here would be a way to classify the possibilities and phrase it as a theorem. You say, here are 3 assumptions, and then there's also the relativity of simultaneity. First assumption is you say the beam splitter can prepare any upper branch probability P. They say every pure state with the same probability can be prepared by doing locally reversible operations. And then whatever Alice and Bob can do should be isomorphic. And then you find that the dimension of the Bloch ball can basically be 1, 2, 3, or 5. So this includes 3, which is what we have in our world. 5 would also be possible, and then 1 would be a classical bit where you just have classical missing knowledge where the particle is in one number or the other, and 2 is quantum theory over the real numbers. And it's important to see that these 3 assumptions, A1, A2, A3, they allow all Bloch ball dimensions whatsoever. It's only a relativity of simultaneity, when you put that in addition, that brings you down to only these 4 possibilities for what your bit state space can be. Right. Good. So that was the first thought experiment. Any questions on that part?
To understand a bit better, so I should imagine all that you said, so you don't have 2 qubits, right? And one goes to above, one goes to RCA.
Yep.
So are you putting it in a state that is spatially very dislocated?
Yes, it's like an effective 2-dimensional Hilbert space. It's a subspace of Fock space. We have like 1 particle here, 0 there, or a 0 particle here and 1 there. Right. Yeah. So this is supposed to be an effective qubit or something like this.
The operation TA and TB depend on the observer.
Yeah.
If you change the simultaneity, you might change TA and TB.
Yes, so you have to be a bit careful what you mean by relativity of simultaneity here. So first of all, just regardless of a frame of reference, when you're in any kind of frame of reference, you might, for symmetry reasons, just say, well, whatever A can do, there should be an analogous operation for B. This is the one assumption I put here, that the groups of things they can do should be isomorphic as groups. Then you have to sit down a bit and ask what could be the possible transformations when you go from one reference frame to the other. But then what you find is that the 2 labels, being up or down, they are degrees of freedom that are not really geometric in nature. I'm not really saying, do I have this coordinate or that coordinate, but it have actually physical arms of my interferometer that are labeled physically, which breaks fundamentally Lorentz invariance, which is why you have basically the trivial representation in the end. Yeah. But yeah, maybe we'll take a bit more time to go into detail with this. Yeah. But.
Does this R thing, does it depend on how many dimensions in space-time?
No, doesn't follow right now. It's tempting to say it's a 3-dimensional Bloch ball in the end, so maybe these sigma x, y, and z have something to do with the dimensional space-time, but that's another story. Here it's just d-dimensional in Minkowski, or even weaker, you just have a relativity of simultaneity. Okay, maybe I go on from this for now, and just tell you a bit about some work in progress with Marius. I told you about the set of correlations, and that the quantum subset is strangely in between the classical and the quantum correlations. Now, it has been a long-standing open problem in the field of quantum foundations to say, how do you characterize this boundary here, the correlations that can be realized in quantum theory? Computationally, you can ask the question, and then Miguel, who was sitting here too, find a nice method to do that. But what you want is physical principles that tell you why you cannot have more general correlations than the quantum ones. And our idea here is to say, well, here's the quantum information picture, where you have locally always black boxes, your state is a black box, your outcomes are just labels. But in fact, generally we have more information. Typically we measure, for example, polarization or spin, which is a geometric degree of freedom. Could it be that this gives you extra constraints on the possible correlations? And now, first of all, we have a bad news. In general, it doesn't give you much constraints. You can have something like a science fiction polarizer. So you have a science fiction polarizer, you give one of them to Alice, the other one to Bob, and they can both choose angles alpha and beta. And then the outcome probabilities for plus plus or plus minus and so on would be given by some trigonometric polynomial. Now this would be a stronger than quantum correlation. So this would be a polarizer that you cannot realize in quantum theory. But it turns out, if you assume a bit more and say, let's assume that the local expectation values that I compute in this form, when I put them into a vector, that this vector transforms like a standard vector in space. So if I rotate the axis, then the probability vector should also be rotated. If you do that, then it turns out that all the correlations that you see in this experiment must automatically be quantum. And vice versa, it's exactly the quantum bare correlations for two parties, two outcomes, two measurements that you can get satisfying this constraint. So symmetry on your local probabilities basically determines the quantum correlations, in this case, without assuming quantum theory. Okay, yeah, and also it tells you that these correlations cannot be classical. Classically, you could not have the symmetry that a local rotation of a device determines the probability of an outcome. So we hope to use this actually to certify quantumness or do something like that with it. Okay. So in a way, this was all going in one direction. We had assumptions on space-time, and this gave us constraints on the probabilities. Now the question is, can we go the other way around? And this is now work with Philip, where we try to do this to some extent. And well, this fits maybe a bit so indirectly in this paradigm of understanding space-time via quantum information. We have other experts, of course, here in the audience. But what we ask here is only a very particular question, namely, what about the symmetry group of space-time, the Lorentz group? Can we maybe understand this symmetry group from a quantum information perspective? And the answer will be yes, in some sense, and under some auxiliary conditions. And how much time do I actually have? 15 minutes or so? Then, okay. Then I will try to go through this, where I just show you another thought experiment, and then what it means for quantum states, and then actually derive something about the Lorentz group and how that plays out in physics when you fly by in a spaceship with a Stern-Gerlach device, maybe. Okay, so what's the general setup? We have two observers, Alice and Bob, physicists that are very far away, and they have their local laboratories. And they have never met before, so they have not set up a common frame of reference. But maybe they can talk to each other on the telephone and exchange classical information. Now, here's something they may want to do. Maybe Alice calls Bob on the phone and asks, hey, Bob, can you please send me the following physical object? And then describes some physical object. And then Bob says, yeah, okay, I will try my best, and will use this device to prepare the object and sends it over to Alice. Something like this. Okay, and maybe this will all succeed and they are both happy. But then the problem, okay, the goal is really to send the correct physical object. So they are corroborating and really trying to make this work. But the problem is, of course, if Alice and Bob have not met before, then they will not share a common frame of reference. What this means is that if Alice sends her description to Bob and encodes the description of the object somehow, then Bob will just not in general know what frame of reference Alice is using. He doesn't know, and he will send the wrong object, and then Alice will not be happy. It's a very, very boring game in a way. Why is that? So the reason for that is that basically the two here, Alice and Bob, can choose different encodings of a physical property into mathematical descriptions, which is nothing but a reference frame. So maybe Alice describes the spinning ball by some coordinates that coming from some map phi A, Bob by some map phi B, and then these are not identical, but there's a transformation that relates the two. And they can use this transformation to actually swap between the two descriptions. So Alice sends out her description, then this transformation will just swap her description into one that of Bob's coordinate system, like this. And then Bob knows what state Alice means, and then Bob can send the correct object, and then they're done. So it's something like this transformation that we have to do is something like the gap between the two, the reference frame gap or the information gap between these laboratories. And what they want is they want to make this gap, in a sense, as small as possible. And maybe this becomes clear with a very simple example. So maybe Alice wants Bob to send a spinning billiard ball. It's a bit, you pack it into a box and you hope it's still spinning after the mail delivered it to Bob. But you can try to do that. And here's a very stupid strategy that they should not do. Namely, Alice could just use an arbitrary curvilinear coordinate system to encode the spinning direction into a vector and write it on a piece of paper. And then Bob uses just another arbitrary curvilinear coordinate system. And then all you can say is about the descriptions that are related by an arbitrary continuous map, by a homeomorphism. And this is, of course, a very, very general map. And so it's very stupid to do that and has to choose so different descriptions. But physics allows them to do something better. A better strategy would be to say, well, both of them should use inertial frame reference systems to encode what they have. And in this case, that both use inertial frame, we know that what relates the two is actually a Galilei transformation. Galilei transformation is much simpler. It's a smaller group of transformations. So in general, you would have a strategy where both agree to use the encoding from a small set of possible encodings. It's kind of physically natural and as small as possible, and somehow physically distinguished, that physics allows them to use this and not another one. Pardon?
Why is it Galilei and not Lorentz?
So this is just formulated, say, in classical physics for now. Yeah, like that's why billiard ball, but this looks like an atom. Yeah. So in classical physics, you would have a Galilei transformation, depending on what other assumptions, auxiliary assumptions you take. So the first thing you can actually show is that you have a property that if three encodings are physically distinguished, then also this combination should be physically distinguished, which tells you that these transformations here that map one description to the other, that these transformations form a group, like the Galilei group. So this is true in general, always in this scenario. And then you can ask, is there always somehow a best strategy in the sense of a smallest group? And in fact, you can throw in the theorem that in this setup, whatever physical assumptions you put and whatever you want to send, there's always a kind of unique smallest group that relates A and B. So the best possible description that they can agree upon, which would in classical physics be something like the Galilei group. Good. Yeah. So the summary here is you have this game you want to play, you want to win it, you have to correct your description with a transformation, and then there is a smallest group of transformations that you have to put in between to make the game succeed. Good. Good. Now, we see also in classical physics, before I come to the quantum case, we see that first of all, well, different physical objects come with the different groups. So if I send a spinning billiard ball, this will be something different from me wanting to send, I don't know, some other physical system. Sorry. But it turns out that often the different objects that you can want to send, that they hang together in a sense. For example, here's an object, which is just the spinning direction of a ball in classical mechanics. Here's another object, which is doesn't have so many symmetries, and it's characterized by 3 orthogonal axes. And the thing is, if you know how to send objects of that kind, you also know how to send objects of this kind. So there's one Galilei transformation that basically works for both of them. And if this is the case, we say that they hang together somehow. Good. And what they have to do is they only have to find the correcting transformations in between them for one of these objects, and then they get it for free for all the others that hang together. And if this is true for many objects, now I know to send billiard balls, and we've agreed on a description, I know to send rockets and stones and whatnot, and we all agree on our respective descriptions, then we can talk about having set up a common reference frame. It's like an operational definition of what that means. Good. Now what about quantum states? What if you communicate quantum states? Alice asks Bob, now Bob, please send me the following quantum state. And it could be a density matrix, like this one, for example. But then the problem, of course, is Bob doesn't know what Alice means because they have not agreed on a Hilbert space basis, which is a problem, and they have to correct for this problem. So they may choose different encodings of quantum states into density matrices, but they cannot agree on a basis of this encoding over the telephone. A priori, this means that the descriptions will be related by a unitary, so Bob's description is a unitary transformation of Alice's, or maybe even an anti-unitary one. And then you would have the full unitary group that relates the laboratories between A and B. But this is a very big group. This would mean for every Hilbert space that they choose, they always have to find a unitary that relates the Hilbert space bases into each other. Can they do better? And the answer is yes, they can actually do better than that. And what you need for that is something we have in our world, which is a universal measurement device. Typically, when you have a measurement device, we think of, oh, we can input a certain physical system, we get a number of outcomes. And now universal means that you have a device where you can input two different kinds of systems, and you can look at the outcomes. So an example would be a Stern-Gerlach device, where this here measures spin in z direction. And you know that this works for spin 1/2 particles, where you would have an observable, which is a 2x2 matrix, that's actually performed by the device, or a spin 1 particle or any other particle. Yeah? So that works universally for a couple of different Hilbert spaces. It doesn't have to be a geometric observable. Just think of a device that does this and that measures different Hilbert spaces, and one observable in different Hilbert spaces. Now, how do you define that abstractly? Well, you want to say something like, oh, here's spin z measurement. That's a universal measurement that measures it on two different systems. But here, that would not be universal. I input a particle, and if it's spin 1/2, I measure in z direction. If it's spin 1, I measure in x direction. That would be that's not a universal measurement device. And what you do is you say, oh, what I have to do is I have to say, what does it mean to measure one observable in different Hilbert spaces? Yeah. And so you write down a bunch of consistency conditions. You say, if I measure this observable on a system, and if I measure it on another Hilbert space, another physical system, then this map in between the two should be continuous. The order of observables, which one is larger than the other in expectation value, that should be preserved among switching the different systems. And there's something like a distinguished zero measurement, where I basically do not measure, but output 0 all the time. So this is something that defines what you mean by universal measurement devices. Now, if you have two Hilbert spaces, and there are lots and lots and lots of observables that you can measure jointly on both of them, then we say that they hang together. Yeah? They're a bit like the example before. So like the spinning billiard ball and the physical object. Okay, let's maybe skip this. Now, what does it mean? It means, for example, that Alice and Bob, when they know how to send physical systems S to each other successfully with the correct transformation in between, say spin 1/2 particles, for example, then they automatically also know how to send physical systems of another kind, for example, spin 1 particles. If they are universally measurable for many such devices, then they can do this. They only have to agree on one system, and they automatically know how to send systems of the other kind. And if you have that, and you say, well, maybe all finite dimensional quantum systems actually hang together, which is the best possible situation you can have, then all you have to do is find a transformation that corrects for the smallest one, the smallest dimensional quantum system, like a qubit. And then once you know how to send qubits, you know how to send everything, and you have established a reference frame. So we had these consistency conditions here, and if you look at those consistency conditions, and you ask, how are observables on two different systems related to each other? Given that I want this consistency condition, then you find that they are related by conjugation with an invertible matrix. And so maybe, how should I say that? So let's say, okay, so here, if for states, this would mean that if Alice assigns state rho, then Bob would assign x rho, x dagger to a state. Now we make one further assumption, namely the smallest quantum systems for which this works is actually a qubit, as I said before. So it's a two-dimensional system, but we think we can actually get rid of this assumption with some group theory. But if you do that, then you will find that this minimal group that relates the reference frames between A and B is a product of a scaling factor and the orthochronous Lorentz group. So, what do these factors mean? So what is this factor R plus here? Well, the factor R plus you can understand as somehow relating the different units that Alice and Bob use for the observables, maybe miles versus kilometers. There's the conversion factor in between. And then we have the Lorentz group sitting here, which should give the rest of the relative reference frame. Now, how can we interpret that? Does it have a space-time interpretation, maybe? I'll come to that in one slide. First, let me tell you a bit more. So we get a general theorem which doesn't only tell you that you get the Lorentz group that relates the observables between them, but you also get that the different physical systems carry representations of SO3. So you get something like spin representations on the physical systems. And also of the Lorentz group, which acts by conjugation with a matrix. Now you can say, what does all that mean? This is somehow a non-unitary transformation, and so how do we interpret this physically? The idea is here that this X is actually mapping between two Hilbert spaces. So it's not unitary, but it's an isometry. It also changes the inner product for the two Hilbert spaces. But let me actually give you a more colorful picture of that. Here, so this is a physical picture that describes what we found. So you have an observable M, and the observable will be described by Alice as some matrix. Here's a matrix that uses Bob to describe the observable, and they are related by conjugation with an SL2Z matrix. What physical situation would describe this? It would describe a Stern-Gerlach device where Alice, for example, is at rest and some observable is measured, and then Bob is flying by with a spaceship and views this measurement device maybe from a relativistic reference frame. Now, if Bob is also at rest and just rotated, then the observables would be related by unitary, but if he's very fast, so if it's in the relativistic regime, then he will actually see two different eigenvalues. So Alice may see some deflection upwards and some deflection downwards, whereas Bob may see a stronger deflection downwards than upwards, which means also that your eigenvalues change in your matrix, which is why you have a non-unitary transformation between the two.
Stronger deflection. I mean, there's a discrete number of outcomes.
That's right.
Aren't the probabilities that we're talking about counting the number of atoms that went one way versus the other?
Yes.
Observers would agree on the count ratio, regardless of the speed.
No, it's a good question. So what you can do is so in the way this is written, what this means is you have an observable and it has two eigenvalues, and the eigenvalues are now the deflections you see along your screen of simultaneity. So you have your spin 1/2 system. It's a wave packet that travels through a magnet. And then if you're Alice here, you say, oh, I imagine the screen here where I look at both wave packets at the same time. And then I ask, how far is this upwards deflected in some unit of length? How far is this downwards deflected? And then you find maybe plus x and minus x as two possible eigenvalues. This would define you an observable. And it's true, if you send single particles, you get probabilities, but you can also ask about the expectation value of this observable that I've just described. And then you would have MA as your matrix of the observable. But if you fly by in a spaceship, then your screen of simultaneity would be tilted. And so you would say, well, for me, at the same time, this particle would be further down than the other one, so the two eigenvalues would not be the same, they could change as well, which is reflected in the non-unitarity of this map here. But you will, for example, always see positive and negative deflections, which follows from this being an SL2C.
That doesn't sound like the correct way to relativistically transform spin.
Yeah, so, I mean, more formally, what you have here is you pick out really only this 1 degree of freedom that you're interested in. More generally, what you say is that you map a state to another state from Hilbert space for momentum P to another Hilbert space, which would describe the boosted momentum. And then this X would describe basically an isometry between these two Hilbert spaces. So I'm probably running out of time, but maybe we can talk about this after the talk.
Can I just quickly intervene? Because so the observables here that transform in this manner, in this non-unitary manner, are actually sort of hybrid observables in this example, which has a classical part and a quantum part. The quantum part is the discrete part that gives what is deflected up and down, and the classical part that transforms in this way, which is given here in the slides, is actually something like the Four acceleration experienced by the particle in the magnet. And this Four acceleration is seen differently by different observers, and that's the part that transforms then under the Lorentz group. So it's not, so this observable is not just discrete outcomes, but it's also about the acceleration. So and that's why it should also be non-unitary, because different observers won't agree on this acceleration.
Okay. Good, so I should probably wrap up. For the last part, one way to see what's been done here is to say, here's the usual line of reasoning. We assume that we have relativistic 3+1 spacetime. From that we derive, together with quantum theory, that we have, well, first that we have the symmetry group, the Lorentz group, that we have representations of spin on the different quantum systems, and that we have these devices that function in a universal way, like Stern-Gerlach devices do. But what we did was to reverse this to some extent. We say, let's assume we have enough devices that operationally function in this universal way, together with auxiliary assumptions, like n equal to 2, that the smallest system that you can feed in here is a qubit. And from that, you derive the other way around, that the operational symmetry group that relates laboratories should be the Lorentz group, basically, and that you get representations of SO3 on your quantum system. So you do not get space-time, but you get the symmetry group as a group that relates to observers, how they describe the local quantum physics. Good, that's the final summary, but let me really just stop here. So here are the two of the papers, and thank you for the attention.